Hi, everybody. This is Mrs. Case, and thanks for joining me today as we continue exploring exponential functions. Our last lesson was lesson 7.5, where you learned the beginning of growth and decay exponential functions, and you did some modeling. Well, we're going to go ahead and continue working with that. And at the end of Mrs. McCarthy's lesson, she alluded to what we would be doing in this lesson. So let's take a look real quick at our objective. What's different today is we're going to be calculating growth and decay rates in order to then write our growth and decay functions and make predictions. So these three things I've highlighted, you've already done the second and the third. What's going to be new for us is we'll calculate the growth and decay rates because those aren't always given to us. The supplies you're going to need are the 7.6 notes, and that's in page 13 and 14 in packet number 4. And I'll give you a link if you need to download that and print it. You can go ahead and do that. You definitely are going to need your TI calculator again today. And the activities in this lesson are a warm-up. We've got a video. I'll try and make it as brief as I can. We're not going to go through every problem that's going to be on that worksheet, but we're going to hit a majority of them. And then make sure you watch this video all the way to the end so you do get credit in Schoology. We don't actually go through and award points and enter this into the grade book. It's a process between PlayPosit and Schoology. So you must finish the video in order for PlayPosit to speak to Schoology and award those points. Now, your homework or your practice today is going to be quizzes, and we haven't done one of those in a while. They're kind of fun. You're going to use your calculator and look at growth and decay in terms of calculating rates and making predictions and different problems along the lines that we've covered over the last couple of lessons. When you work in quizzes, you do not have to upload any work. We're going to go ahead and log in on our side. From the teacher side, we'll see your work, we'll see your scores, and then we will enter your grades. So that's what our day is looking like. Let's go ahead and see if we can get this moving along. And here's our notes for today. Remember, what I told you is different is we're going to be calculating rates. But before we get into that, you know what I'd really like to do is go back and write out that exponential equation that you were working with earlier in the week. And we know that the value at a given time or the population at a given time, and both of these have to do with growth, start with A, and A is our original amount, times that growth factor, which is 1 plus R raised to the T. And when we look at R, if R is positive, we're looking at an increase. And that's going to be growth. If R is negative, we're looking at a decrease, and that's going to be decay. And so when we have 1 plus R, that's no longer our rate, that becomes our growth factor. Or 1 minus R, that's no longer just the rate, decreasing rate. 1 minus R, that becomes our decay factor. So we can talk about positive or negative R, and both of those relate to the growth factor, whether we're going to work with growth or decay. And so another way we can combine those together is call that 1 plus or minus R raised to the T. When we say plus or minus, we really are talking about, is this growth or is this decay? So I'm just going to go ahead and add that back in there. Okay, so let's go ahead and get started with calculating R. Looking at problem number 1, calculate a percent increase. So I'm going to grab my highlighter here real quick. Calculate a percent increase. A population increases from 1,000 to 1,200 in 1 year. What is the percent change in that population? What is the growth rate? Growth rate is really the same as the percent of change. So we have a very simple formula to follow. And that simple formula just says that we're going to calculate the change in the population, the change And then we're going to divide that change by the original value. So the change in the population went from 1,000 to 1,200. All we have to do, I know you're looking at that and saying, that's a change of 200, Mrs. Case. Why are we doing any work here? Well, sometimes it's not quite that intuitive. So we're going to go ahead and subtract. And then we're going to divide by the original population, which is 1,000. And let's see, 1,200 minus 1,000 gives me a change. We saw a change of 200 people in, let's see, and we're going to divide that by the original 1,000. That gives us a 0.2. And that is our growth rate. Now, how do I know that's a growth rate? Because the problem was about increase. We increased from 1,000 to 1,200. And so there's our rate right there. And it's a positive rate. We can do the same thing when we're talking about decrease. Remember, all we're doing here is just calculating the rate. Okay, calculating a percent decrease. In this problem, a car loses its value from $20,000 to $18,750 from one year to the next. What is the percent change? When we see percent change, we're really asking what is the growth or what is the decay rate? So percent change, again, it follows a really simple formula. And that simple formula is the change in the rate divided by the original. Okay, so we've got the 20,000 minus 18,750, and we're going to divide that by the original, which is going to be 20,000. Grab our calculators, divide it all out, and I'm not going to round this number. If you notice, this number ends after 4 decimal places, so I'm not going to round this. I'm going to use the entire number, 0.0625. That's 625 10,000ths. And in this case, this is R. So we're going to continue working with these problems, and I want you to remember the formula that we used is just the change divided by the original, and that's going to give us R. So let's go ahead and move on and now apply this information. Taking a look at problem number 3. The population of a city has decreased from 30,000 in year 2000 to 27,000 in year 2001. And we're asked, what's the growth or decay rate? Well, already it's told us that we're working with a decrease. Let's go back and highlight the information we need. It's telling me that we've got a decrease. Now that decrease means I'm going to be working with a decay. I know I'm going to be working with decay because we see the population moving down. It started at 30,000 and it went to 27,000. So let's go ahead and get some of the numbers that we're going to need. We know that the original number is going to start out at right here. A is 30,000. Now let's go ahead and find R. When we work with R is going to be the change. Remember the triangle delta? Delta means the change in the population over the original. So we're going to take 30,000 and minus 27,000, and we're going to divide that by the original 30,000. 37 minus 27,000 gives me 3,000 divided by 30,000, and that is 0.1 or 1/10. There is my rate. Now, is this rate of increase or rate of decrease? The problem tells me it's a decrease. This is a decay problem. So let's keep going. Write the function for the population. Okay, so we remember exactly how to write these functions. This is a population problem. So the population at time t is going to be, let's see, our original amount Now I need that growth factor or decay factor. In this case, it's a decay. We're decreasing, so it's decay. And so I'm going to take 1 minus r raised to the t. And we're going to keep going. If the function for this particular problem, the population at time t is the amount, the original amount, one minus 0.1 to the t. And I'm just going to keep going. The population, I'm going to simplify this, is 30,000. And let's see, 1 minus 1/10 is 0.9 raised to the t power. So here's my answer for part B. Here's my answer for part B. The function for the prediction of the future. And we see that we are decreasing. We're from 30,000 down to 27,000. So it's going to just keep decaying. What was the growth factor? Well, or growth or decay factor. In this case, we're going to be looking at decay. We already said it was going to be decay because we were decreasing, decay, decay. The decay rate, our decay rate ends up being 1/10. But we're not adding, we're subtracting. So then what does the decay factor end up being? The decay factor would be the 1 minus 0.1, which gives us the 0.9. And we see that showing up right here in our function. The next thing we're asked to do is calculate what's the predicted population in 2022. So we need to know what is the time. And in this case, the time, we're going to start with, let's see, we want to know the time in 2022 when we actually started in 2000. And we see that that's going to be 22 years. So let's go over and use our function. The population in 22 years is going to be 30,000. 0.9 raised to the 22. So let's grab our calculators and see if we can't. Let's see if I can drag this over a little bit. Oops, I lost my calculator. Okay, we're going to take 30,000. And we're going to multiply that times the decay factor, which was 0.9. Now we know that's decay because it's less than 1. And just the decay factor is going to be raised to the power of 22. And so we see that that's dropped down to 2,954.312707 people. And we know from the lesson last week that we're not going to use a portion of a person. We'll just round that to the nearest whole number. And that's 2,954. The population in 22 years would be 2,954 people, if that's going to continue to drop at the same rate. So population at 22 years was 2,954 people. Okay, and that was our decay problem. If you need to catch up on your notes, go ahead and pause the video. Otherwise, let's go ahead and move on and we'll get you set up to solve the next problem. Let's go ahead and see what this problem's about. I'm going to get my highlighter, get ready to highlight what seems important or pertinent. Number 4, the value of a car decreases from $25,000 in 2010 to $20,000 in 2011. So it's dropped down $5,000 in a year. Is this growth or decay? Well, it told me that we're decreasing, so I know that we're working with decay. I know it's decay because we were told this is a decreasing problem. So let's go figure out some items. First thing I know is the initial amount is A. That's $25,000. And when we go to write our function, the value at time t is going to be the original amount times that growth or decay factor. In this case, since it's decay, it's decreasing, it's 1 minus the rate, all raised to the t. And that 1 minus r, that's our decay factor. So let's see if we can get this set up for you. We're going to go ahead and set up the decay rate. R is going to be the change divided by the original. And then you're going to write the function. Was this growth or decay on part C? We know it's decay because we've already talked about decrease, and we want to know what that decay factor is. So let's have you go ahead and start working through the problem, and once you figure out what your function is, let's go back and predict what's the value of the car in 2022. So our time, 2022, and we're going to subtract our original starting time, which was in 2010. We started in 2010. So how many years are we looking at? We're looking at 12 years. So once you've calculated your function, then I want you to find the value at 12 years. So let's go ahead and get some things set up. We know that what A equals. You're going to calculate R, and then you're going to write your equation. Write your equation, and then calculate the value at 12 years. So let's take a look. How did this work out for you? You were asked to find the growth or decay rate. We know it's decay because we were told the value is decreasing, so that's going to be decay. We subtracted out the original minus the secondary value, and we ended up with 5,000 divided by 25,000, which was 0.2. That's going to be the rate, and that's the decay rate. So that's going to equal the decay rate. Write a function for the value. Let's see, the value at time t is going to start with that original amount, 25,000, and then I have 1 minus r. That becomes 1 minus 0.2. That becomes the decay factor. When I subtract the rate from 1, I have a decay factor of 0.8, and I'm going to raise that 0.8 to t, the t value. That becomes the function for the value of the car in the future. What is the growth or decay factor? We just talked about that. That's the 1 minus the rate. The decay factor is going to be 0.8. And we know that's decay because whenever this number that follows the original amount, if this number is less than 1, then we're working with decay. If it's greater than 1, we're working with growth. And then part D asked about the predicted value excuse me, in the year 2022. So we needed to know how many years are we talking about. Since the car was purchased in 2010, we subtract to find we're looking at what's the value at 12 years. And so we're just going to substitute the t in, or 12 for t into our function up here, and we're going to start with 25,000 times 8 raised to the 12th power. And that means after 12 years, that car is worth $1,717.98 if it continues to decay or decrease in value at that same amount. So I hope you did pretty well with that. If you need to go back and look at the problem, then go ahead and do so. But we're going to go ahead and move on. Let's take a look at number 5. Again, I'm going to help you get it set up and then leave you to get to work on it. The value of an antique car has increased. This time we're talking about increase from $40,000 to $45,000 from the year 2012 to 2013. So in 1 year, from 2012 to 2013, it's increased by $5,000. So let's go ahead and get our function. The value at time t is going to be the original value, and 1 plus or minus the rate. There becomes our growth or decay factor raised to the t power. Now we have to determine, based on the way the problem's worded, is that going to be growth or decay? The value of the antique car has increased. That's going to be growth. Since that's going to be growth, I'm going to be adding 1 plus r, not 1 minus r in this case. So let's go ahead and start working on getting this set up. What was your decay rate? I want you to go ahead and calculate your rate, the change divided by the original. Then write the function, and I've got it set up for you over here. Answer, what is the decay factor? Remember, the decay factor is when you start with 1 plus r or 1 minus r. And after you've answered those, let's go ahead and calculate the value of the car, the value at what year? The value of the car at what year? At 2025, we started at the original value, at the original time of 12 years. 2012, so let's subtract 2012 from 2025. We're talking about 13 years. T equals 13. So then go calculate the value at 13 years. And we'll come back in just a minute and check those answers. Well, let's take a look at your work. How did things turn out for you? First thing we had to go talk about was calculating up the growth or decay rate. And we knew it was growth because we saw the value of the cars increasing from 40,000 to 45,000. And so we find the difference between, the change between those two values just by subtraction was 5,000 divided by 40,000. And our growth rate is 0.125 or 125 thousandths. We're going to take that growth rate and we're going to add 1 to it. 1 plus the rate. Now that becomes the factor. Once we've added rate to 1 or we've subtracted rate from 1, we're getting the factor, the growth or decay. But this time we're working with a growth factor. So the function that we're working with ends up being, let's see, we'll start right here with our original base that we worked on earlier in the week. The value at any time is the original amount, which was 40,000, and now I'm bringing in 1 plus the growth rate, which gives me the growth factor. We write the final equation in terms of the growth factor. So if I want to find the predicted value of that car, remember, it had a $40,000 value in 2012. What would be the predicted value if it continues to increase along this rate? And if that rate is consistent 13 years from now, when we subtracted earlier together to find that was 13 years we're looking for in our time, 40,000 times the growth factor of 1.125 raised up to the 13th power. That car that was worth $40,000 in the year 2012, by the year 2025 is now worth $184,945.08. That sounds like a great investment to me. If you need to pause and catch up on any part of this, go ahead and do so. Otherwise, we're going to go ahead and take a look at number 7. So flip the page over. We're skipping number 6. Number 6 is more of the same 3, 4, 5. 6 was real similar. Let's go take a look at the graph on number 7. And I want to get my highlighter ready to go. The graph represents a half-life of waste from a nuclear plant. And a lot of times in chemistry problems, when you all get to chemistry, you're going to work with half-life quite a bit. So we're looking with half-life. Oops, let me get my highlighter. Half-life. After a specific amount of time, the amount of waste decreases by half. After each half-life cycle, the waste decreases again by half. So let's take a look at what we're looking at. At our x-axis, It looks like we're looking at the number of half-life cycles. It doesn't tell me how many years that is. It doesn't necessarily mean it's 1 year, 2 year, 3 years. It might be 45 years, there's one cycle, and another 45 years is a second cycle, and another 45 is another cycle. I don't know at this point what that half-life time is, but that's okay. We just know it's going to be decreasing. Now let's look at the y-axis, the amount of the radioactive material that remains. So we want to start off with time zero. At time zero, there are 240 units of this radioactive material. And then we can see that at time one, it's decreased to half. 240 divided by 2 is 120. After the second cycle, it's decreased. That 120 divided by 2, it's decreased down to 60. And then there's another one of those cycles. And 60 divided by 2 takes me down to 30. And 30 divided by 2, and so on, and so on, and so on. And we're going to see that it's just going to continue to get closer and closer and closer to an amount of 0. Okay, so let's start reading. Part A. If T represents the number of half-life cycles that have passed, write an equation that can be used to determine the amount of radioactive material after T half-lives. Okay, so what we need to know is, it almost seems like we don't have enough information, but we really do. How do we write these equations? We write these equations by saying that the amount, the value or the population, is going to be the original amount times the growth factor or the decay factor. This is actually going to be our decay factor. You know, when we say 1 minus r, and then we're going to raise it to t. So let's take a look what we have. And we're going to name our function r of t, the amount of radioactive material that is left over. It's going to start out with the original amount, which we see over here was 240 units. And it's decreasing by half. So if it's decreasing by half, my rate is 1/2. 1 minus 1/2, if the rate is 1/2, then the factor is 1 minus 1/2, and the decay factor is just simply 1/2. Both the rate and the decay factor are going to be 1/2. So let's see. I'm going to go ahead and multiply that times half-life. And I'll give you a hint. Whenever you're working with half-life, it's not really difficult. You take the original and you multiply it times 1/2. And then you raise that to the t power. Okay, so now we're asked to find the domain and the range in context of the problem. Our domain are the x values. So let's see what x is about, and our range are the y values. X talks about how many half-lives are going to occur. Well, we start at 0, and we can see at 1, it's decreased, at 2 it's decreased, and 3, and 4, and 5, and 6. And you know, it looks like it gets down to 0, but it never really does. With half-life, you keep dividing a number in half, and half, and half, and it gets very, very, very close to 0, but it never really ends. So ideally, this is really just going to go on to infinity. So my domain is going to be between 0, and that's inclusive, to infinity. And that represents the number of half-lives. That's our context, is our half-lives. How many of those cycles are there? And now we're going to go take a look at the range, and the range are our y values, and that's just the amount of the radioactive material remaining. Well, we started out with 240, and it's ultimately going to get down very, very close to 0. It looks like it's 0, but you're just taking very small numbers and dividing by 2 and dividing by 2 and dividing by 2, and it's going to get very close to 0, but it's actually never going to get to 0. So we're going to go ahead and say that it's 0 to 240, and we're going to include that 240 because we actually started with 240, and that's the amount of radioactive materials. Okay. And then part C asks us, as the value of T increases, that's the number of half-lives, as these keep increasing, what becomes R of T? Well, as T keeps increasing, what becomes R of T? Let's see if we can pull up our calculator real quick and do something with our calculator. I'm going to go ahead and clear this out. And let's put this equation into our equation editor under y equals. Let's go ahead and put in 240, parenthesis, 1/2. I'm going to call it 0.5. And I'm going to now raise this up to, with the caret to the t power. And I'm going to go back up to my variable function key. And we usually use x, but there's t. It's sitting right there. Okay. Now, let's go take a look at not the graph. We see the graph on our paper. Well, let's go look at the table. So second graph gives me my table. And the question is, as x increases, what becomes with y? What becomes to the radioactive amount? As t increases, what is the radioactive level left over? So let's just keep scrolling down. We see these numbers are all graphed. And remember, I told you we're taking numbers and we're just dividing by 2, divide by 2, divide by 2. Where do they ultimately go? Where do they seem like they're going? Oh, we've gone into scientific notation. Let's move our calculator over. And you recall what these numbers in scientific notation mean is that they're very, very small numbers and we're dividing by 0. And we're dividing by 2. No such thing as dividing by 0. Dividing by 2 and dividing by 2. And we're getting closer and closer and closer to 0. And we can see that happening. So let's go ahead and minimize that real quick. And we see that as the value increases, the radioactive material is approaching. How much material is left? It's approaching 0. Okay, so that's half-life, and looking at a function, a realistic function that occurs many, many times in the area of science. Now, there's just one last problem I'd like us to take a look at, and that's analyzing a function a little bit. So we're going to skip number 8, we're going to go down to number 9, and we're going to skip number 10. So let's take a quick look at this problem and see what's going on. I'm going to grab my highlighter. And it says Jenna put $800 in the bank in 2015. Fantastic for Jenna. She invested some money. Someone showed Jenna an equation that represents her savings over time. And here's her equation. Okay. So the value in the account is 800 times 1.03 raised to the t power. And that looks like an exponential growth or decay. Which is it, growth or decay? I want you thinking about that real quick. And let's go into some of these questions. Okay, so we know that we look at the value. Oops, gotta go grab my pen. The value at time is the original amount. Sorry about that, big dog. Guess she saw someone out there, probably a squirrel. Raised to the t power. And let's see if we can start matching some things up. 800. 800 is A. I'm going to go ahead and switch over to my blue pen so you can see this. What's the starting amount? The starting amount is right there at $800. And we know that because we were told she started with $800 and it's showing up in the place of the original amount. Now, what's the growth rate? Not the growth factor, we want the growth rate. Remember, growth rate is going to be this piece, 1 plus or minus R. So what I'm seeing is 1 plus R. 1 plus R equals 1.03. So R has to equal 1.03. Now let's change that over to a percent by moving the decimal 2 places, and that's 3% is the growth rate. Rate is always a percent. What's the growth factor? The growth factor is what occurs when we add 1 to the rate. And we see that growth factor as it's the amount of, the amount each preceding y value gets multiplied by. So the growth factor is the 1.03. There's my growth factor, 1.03. Here's always going to be my original amount. And this number is going to be the growth factor, growth or decay factor, where we've already added or subtracted. Okay, so let me add that in there real quick. How much money does she have in the bank in 2022? Okay, well, let's see. We're going to subtract out 2015 when she started, and that's going to be 7 years. So the value at 7 years, I'm going to let you figure that out. And then how much interest did she earn by 2022? Okay, why don't you go try that out, and we'll get back together in just a minute. Okay, how did your work turn out? We had to just finish up D and E. How much did she have in the bank in 2022? That would have been 7 years after she invested in 2015. So we're going to just simply use the function that we were provided, 800 times 1.03. We're going to multiply that 800 times 1.03 7 different times, and that turns into $983.90. It's a pretty good investment. How much interest did she earn by 2022? Here's a definition for you if you haven't run into interest before. Interest is the total amount of money earned in an investment. So if she started out in 2015 with $800 and at 2022 she had $983.90, we're going to subtract, and that gives us the interest. She had $183.90 interest. So there you have it. We've spent some more time working on exponential growth and decay, and today we calculated our own interest rate, our own rate of changes. I really massacred that. We calculated our own growth and decay rates. So let's take a real quick summary and move on. So when we're working with exponential functions, we want to look at growth and decay rates. Sometimes they call that the percentage of growth and decay that occurs. And we call that a percent change. We can calculate it ourselves by looking at the change in the value divided by the original. I want to remind you that the growth factor is when we add 1 to that rate. The decay factor is when we subtract the rate from 1. We add the rate to 1 to grow. We subtract the rate from 1 to decay. And you can almost assuredly tell whether you're going to be working with growth or decay because this number is going to be greater than 1, whereas if we're working in decay, we're looking at a factor that is less than 1. So our next step is just to move on to your 7.6 homework or practice, as I like to call it, which is quizzes. You're going to find that in the folder. You'll find the link to that. All the work is due by tomorrow at 10 p.m. And if you have any questions, please reach out to your teachers. Y'all take care.